Hello everyone, welcome back to alkaline hydroxide 784, and today in the mathematics series we will be looking at correlation and linear regression. So well, luckily today I am in my right sense of mind so I should be okay. And luckily this topic is pretty easy to talk about, so let's get started. Okay, so what's the first thing that comes to your mind when you say linear regression? Was that okay? I guess some of you probably don't really understand what it is until you actually chance upon the topic. But usually you're reminded of stats, right? Like statistics. Then you see, oh, these two things are correlated to each other. Then you hear that popular phrase that correlation is not equal to causation, something like that, right? Yeah. That's the kind of stuff that comes to your mind. So we get to know more about how this actually works in a bit of detail, I guess. So, well, you have your data, you got your mean, you got all the information that you have. Now you want to put all your information on a chart. So you plot some data on a chart, maybe your physics or chemistry experiment. Also, you could be putting all your values on your graph paper and then trying to find the best fit line, right? Well, this is the computerized version of finding the best fit line, basically. Okay, so of course, since humans are able to find some kind of a best fit line, even though it may not be the best fit line, we do have to be able to tell whether the points that you see there actually have a linear relationship to some extent. So let's say if you so how do you do that? You obviously plot out everything on a scatter diagram here, because here they prefer using a scatter diagram, which you can get from typing down all of the values in your GC and pressing plot, and you will see the points. If you use a cross or something, you can see all little crosses showing each of the points. And that is a scatter diagram because the idea is just that all the points are scattered on the graph and there's no like line or anything drawn on it. So from the scatter diagram you can, I guess there isn't really much to say here, just you see whether the points look like they follow a line, like a diagonal-ish upward trend, or whether they curve in a way. So you can kind of tell whether the points have a linear relationship or a polynomial relationship. And we can look more about that in the subsequent points. But yeah, that's the idea. Okay, so when you draw a scatter diagram, some point that you need to take note of, the beginning and ending points, like the range, basically the range and the domain. So let's say if you have your two variables x and y, and your x goes until 10, you must state down where the 6 and the 10 points are. And likewise for y, you would have like maybe your y is starts from 1 and then goes until 5, then you put 1 and 5 in the places where they're supposed to be in a sense. Yeah, okay. So the next thing that you need to take note of is the correlation coefficient, which is basically that R value that you get when you calculate it in your GC. And what does that do? It's like when you look at it, you will have a sense of how linear it is, right? But you need to show that, like, you need to quantify that value, and that this is what helps you to quantify the so-called correlation between the two things, because I mean, in terms of a linear scale. So you need to. So the idea is that when you have two things compared to each other in a linear scale, would they correlate with each other in a sense? Do they correlate as a linear model? So that's what the R measures in a way. Like what which is a good R and which is not a good R. Basically the R is like it goes from -1 to 1. So -1 would be like negative correlation, which is still a good thing. It's just that it's the opposite. It's like one value increases, the other decreases. That kind of a correlation. If it's 0, that means there's absolutely no correlation between the two. And if it's 1, there's a positive correlation between the two values, that they both increase or they both decrease. So the best correlation occurs near -1 or near 1. So your magnitude of r has to be near 1 or -1. But usually you don't really look at r directly, you usually look at r squared, because that is always going to be positive. So if r squared is near 1, then it's definitely pretty correlated. If it's very near 0, then it's definitely not very correlated, and likely a bunch of fluke that even has a bit of correlation. So yeah, so when you're answering questions, if you get something that's like 0.98, you're good. If it's something that's more like 0.6, then you should say that it's not a very, it's a bit of a weak correlation, but it is there, it's just not that strong. So that's how you express what you see on the calculator. So how do you calculate this whole r and everything that I just mentioned? Okay, I'll tell you how to do it on the GC first. So you have your GC, you can, if you go to the part where you type in all of the values in your table, and you type for x and y, you type all the data points. So each column will have like L1, L2, that kind of thing, right? Is it L1, L2, or is it X? I don't remember the letter that they use, but oh, sorry, x1, x2, I think. So you can actually access that on your calculator itself. Like if you use the alpha button or something, you can see the x1, x2, x3, and you can use that accordingly. And I'll tell you why it's important to have to know that you can use different columns for different things in some time to come. But let me first cover the basic point of doing it. Okay, so once you have that values down, you can plot it as a scatter diagram for your own viewing pleasure, or to actually draw it on your piece of paper. And you can then go to the statistics menu, or whatever way that you have to go to the statistics part, list, like the list that you get. And then you can choose either the y equals to ax plus b, or y equals to bx plus a, or something like that. And then you calculate from there. And once you get that, you can find the a and b and then r as well. So it will tell you all of those three things at once, and you can have a general idea of how linear your model is, and what would be the best fit line to that particular model. Even if it's not that linear, like even the data itself is not that linear, what would be the best fit line that you can get out of that scenario? You can use this to write down the answers to your question, I guess. Like if you know that it's going to be linear, you can use the y equals to ax plus b model, and then just write down the values of a and b. So that's how you get, that's a basic question, I guess, the most basic way of asking this. So how do you look at it conceptually though? Because I mean, you just type everything in GC and let it do all the grunt work for you, but how does it actually work? In statistics, you first take a line, and then you see what's the deviation from the line to the point, like what's the difference. Let's say for x equals to 4, maybe y on the line is 1, and then y on the point is actually 3. So you say, oh, there's a difference of 2. And you do that for each of the lines, and then I think you square the differences, and then you plus them, and then square root that or something. And then you see and then you do that for many other lines until that difference is as small as possible. And that would give you your best fit line. Yeah, that's actually how you get the best fit line. I mean, doing what you do in chemistry or physics isn't really gonna give you the most 100% best fit line, but it's pretty close, I think. Yeah. But this is what the calculator does, or a computer, or whatever machine that you use does to get that particular line, in a sense. The best fit line, in the sense. Okay, so yeah. So that equation of that line is what you get from your y equals to ax plus b. That's the equation of the best fit line. So now we will look at interpolation and extrapolation. So interpolation is using the line to predict a point within the data set range in the sense. So if you look at the first example, from if you have x 6 to 10 and y 1 to 5, you if you're trying to predict a point at, let's say, x equals to 3.5 or something like that. Sorry, not 3.5. Y equals to 3.5, or maybe something like x equals to 7.75 or something like that. But you don't really have a point, like a data point at that particular point, right? So what you do is you use the line to predict what the value of the other variable will be at this value, in a sense. So you can say, oh, at x equals to 7.75, what would y be? And you just use your equation that you got, the ax plus b, or you can use the GC directly to find out what y would be at x. So if you save the equation as one of the y equations in your, the very first screen that you have, where you can type all the equations, if you save it there, then you can just plot that line on your graph itself, and you can use it to find out the value of y for a particular x. It's possible. But if you want to find the value of x for a particular y, you probably have to use the equation that you write down on your piece of paper and then calculate it manually. So that's how you do that equation. Yeah. Or you can just you can use your GC and do some kind of changing the subject to x instead, and then doing something. And then like you type that equation into the GC instead, but that seems a bit extra, so never mind. It's a linear line, so there's no point. Yeah, so that's interpolation. It's within the line, it's within that set of data. Extrapolation is kind of like the same thing, but it's outside the set of data. So extrapolation would be maybe like trying to find out what's the value of y for x equals to 11, which is not it's not within the data set, it's outside the range. So what does that mean? Well, it means that you might be less likely to get a correct answer out of it, like an accurate-ish answer out of it. And you might be wondering, why? If like, let's say all my data is linearly related, and the line shows that how wonderfully linear my data is, how come the data outside the stuff that I collected isn't so accurate? It's likely that this particular local range of data is linear, but it may not be true for the entire set of data. If you think about it this way, like if in a real statistical context, let's say we have, I remember seeing this in all of those library books kind of the thing, and it had data on obesity, and like it showed the example of some graph on obesity in America, and it showed that it was increasing. Well, obviously, yeah. So it was increasing for both the white population and the black population, and at a point of time, it showed that the white population would be 100% obese, and then the black would only be like 70% or something like that. But obviously, the 100% seems a bit too unrealistic, right? It doesn't make sense. So in real life, even though if you were to measure only within a few years, and you see that the data is linear, you may not really realize that over time the data won't be as linear as you expect it to be. Like the overall shape of the graph isn't exactly straight. It may be like an exponential decline, in a sense, like the rate is exponentially declining. In other words, the graph plateaus at a point, or it just doesn't stay linear anymore. So that's why you should be a bit wary about doing extrapolation, and you must be careful to understand that it may not be as accurate as you expect it to be. And it's pretty important to know when you're doing statistics or anything related to this in the future, because this is actually something you might be doing in the future, right? You get some data, you try to find a regression line for it and do all that stuff. So yeah, it's not just for A levels. Anyways, let's move on. Okay, so So now we know how to find do interpolation with the line. We can now go to actual situations and see how we can apply the regression line and all of the interpolation and everything into this situation. So as I meant, the thing I mentioned just now is an actual situation, like measuring the rate of obesity in America, right? So in exam questions, they probably won't ask you that. They'll probably be asking, oh look, my plant is growing this much over this many years, or like my bank account is growing this way. Okay, maybe on the bank account, that's a little bit too consistent. Maybe something more like, yeah, like plant growth or something. And then they ask you to plot the value and then find out how linear or whatever it is and do all that stuff lah. So you just follow the same steps, understand the data, like sorry, understand the question, understand the question, see which is the x value and the y value that you're looking at, see which value influences the other value in a sense. I think you should be able to do that if, especially if you do science, you know which one is the dependent value, the wait, yeah, which one is the dependent value and which one is the independent value, and from there you can put your x and y. So as you change the x, your y will change accordingly. Right, so once you've identified the two values and then you plot them on the graph, and then you can use it to do your interpolation or whatever it is that you need to do it. So, oh yeah, there's a common thing that people face sometimes. Like sometimes they'll ask you to find the value of x given y. In that scenario, do you plot the graph using while switching the x and y values? Like you use the x in your y column and you put the y values in the x column. Well, you don't really do that unless the data doesn't show a clear indication of which one is x and which one is y. If it shows a very clear indication that maybe the time is x and then the height of the plant is y, then you obviously should plot the time as x and the height of the plant as y. You cannot do it the other way around. But if your data is just two random sets of, it looks a bit unrelated in a sense, and you're just trying to see if there's a correlation, then you can use one as x and the other as y, and interchangeably in a sense. So just be careful about that. And yeah, of course, the extrapolation problem is more applicable when you're looking at this particular like practical situations, because sometimes you know that the value can plateau or something like that, and from there you can say, okay, this is not going to be linear forever in the sense. And yeah, the R value will help you tell how good the data is in terms of being modeled by the linear regression line. And in some situations, the data itself doesn't seem linear, but you can still model it by a linear regression model because you can linearize the equation. So how does that work? This will be useful for square, reciprocal, logarithmic, anything that is not too high level polynomial or something. By linearizing it, you're trying to find that y equals to mx plus b kind of a format, like that kind of equation from whatever original equation that you have. So let's say you suspect that this bunch of data looks like a square, like y equals to something x squared plus c. How do you prove that? Well, you literally just did it. Like x squared can be written for x instead. So you imagine instead of typing x into that x column, you type the value of x squared into the column. And from there, you can actually get a linear equation. The end of the story. It's just that instead of having x as your x variable, you're using x squared as your x variable. And likewise for your reciprocal graph, 1 over x, you just try to find something that where the idea is y equals to a 1 over x plus b, and 1 over x is the value that you put into your x column, x column. And for logarithmic, log x, log x, something like that, then I guess you have the idea of how to do it by now. But usually logarithmic would be in a scenario where you have the e to the power of x or something like that, Then you just need to switch from one form to another and then see which one gives you the linear value. So there is a shortcut to typing these values on your graphing calculator, because it's pretty sure you're gonna be pretty sure that you type the original x value in one of your x columns, right? So how do you apply, like how do you change it easily without spending a lot of time? Well, basically you take the, let's say your x value is in x1 and you're trying to put x squared into the column of x2. So you can just type x2 equals to x1 squared, and then you all of the values in x1 will be squared and then put into x2, and you can then just use that as it is. You just input x2 into your, when you're trying to calculate your ax plus b thing, just don't forget to do that, and from there you'll be okay. I think it shouldn't be an issue. Yeah, so just be a bit careful about which one you use as your y and your x columns, because sometimes even the y value has to be manipulated. Maybe instead of y you have to do y squared or something. So you have to be really careful about what values you're putting into the ax plus b calculation. So I think this topic is pretty easy to score in, as long as you're careful and you don't get confused when you're trying to plot all of your values down. I think you will kind of find out if there is a problem or you made a mistake. It'll be pretty obvious because it's very visual. You can tell I can tell that you made a mistake. And then you can try to go and rectify it again, or just redo everything so that you don't have to worry about the mistake again. So yeah, I hope that this is pretty clear. I think this is actually very clear to me. Like, this whole topic is very easy to understand. And this is actually the last topic in the maths H2 maths syllabus. Yay! So what will I be doing next episode? Next episode, I haven't really thought about it yet, but it will probably be something to do with exam strategies or something like that. I know that A levels is already over, but I still need to do this because otherwise the series won't have a conclusion. And if I need a concluding episode or something, I'll do that. If not, we will probably be moving on to a different series, and I hope you look forward to that. Yeah, I hope you enjoyed this series, or at least found it useful thus far. And if you have, please do press the like button and subscribe. With that, I would like to say thank you and bye.